All right, so I think we're ready to get started with our afternoon session, and Hannah's going to talk to us about tagging, querying, and synchronization in QuantumSavory.jl.
Sure. Okay. Hello, everyone. My name's Hannah, and I work for the NSF Center for Quantum Networks, working on Quantum Savory. There are a lot of interesting stuff about this software, but today I'll be talking about how it handles tagging, querying, and synchronization. So, what is Quantum Savory? As some of the previous presentation touched on yesterday, QuantumSavory is a Julia package designed for simulating quantum communications and network protocols. For example, you can use it to model a range of scenarios, such as the one here, quantum repeater setup. So in this case, the goal is to generate high fidelity entanglement between the end nodes, which are the ones over there. We achieved this by first entangling the neighboring nodes and then performing entanglement swapping. And if multiple entanglements are established, we purify them. This entire process can be visualized, and we can also track metrics like the XX and ZZ correlators over time, as shown here. So the software is built with well-structured abstraction layer from low-level to high-level components. For low-level, as Andrew mentioned yesterday, you can plug in any backend simulator. QuantumSavory comes with Quantum Clifford for stabilizer formalism and Quantum Optics for state vector formalism. And above that, it includes a symbolic algebra layer that Andrew also talked about yesterday, and discrete event simulator, which is built with resumable functions and concurrent sim. At a higher level, we have state zoo, circuit zoo, and protocol zoo, which are collections of pre-built quantum components designed to support rapid prototyping of your protocols. But for today, the focus will be on the classical metadata tracker. So let's start with a simple protocol that entangles one slot on register A with one on register B. This is how the visualization looks in QuantumSavory. You can see that the register A has two slots, which are the dark gray boxes. And the first slot is already in use, indicated by the black diamond. So the first step in this protocol is to find an available slot on each register and to create the entanglement. So once you find a pair of free slots, you would like to entangle them. All right, that was very straightforward, but here's the thing. When you look at say slot 2 on register A, how can we know that it's entangled, what it's entangled to? What if we want to know the history of what it was entangled to before? Also, oftentimes we want to apply quantum error correction, which means that we need some sort of mechanism to send classical messages to relevant nodes. All of this can be tracked with a tag. So in QuantumSavory, a tag is an object that represents classical metadata, and it can also be queried. So you can create any generic tag using a descriptor along with associated ints or floats. For the entanglement protocol that I described earlier, we would have entanglement counterpart tag. This tag stores metadata about which node and slot a given qubit is entangled with. Okay, so now let's look at how entangler protocol in the protocol zoo handles finding a free slot. So here we have while loop, and that repeatedly checks for available slots on both node A and node B. If either of them returns nothing, then protocol waits for a fixed amount of time. Here it's 0.1 before trying it again. So in the diagram shown here, node A is full, so the loop continues waiting and rechecking until a slot becomes available, like here. Then once there is a free slot on both side A and B, we can break the while loop and entangle them. I guess entanglement part is not shown in the code here, but so this approach works, but it's not, as you can see, it can be not very efficient. So imagine the gaps are when the querying is being done, like the find free slot functions. And this orange bar here is when a slot becomes free. If the retry interval is too short, the first case, then the entanglement would happen shortly after the slot is freed. But the cost of doing this is pretty high because you're running lots of querying functions. On the other hand, if the retry interval is kind of too long, the second case over here, the entanglement would occur much later than necessary, and it'll cause some delay. Yeah, so ideally, instead of checking repeatedly, we want to wait for like an event and run the querying function then. So to do so, we implemented a new object called semaphore. This is like a custom structure that we built, which multiple processes can wait on simultaneously. So I'm not gonna go into details about how it works, but it uses the lock feature in concurrency. So once the resource becomes available, it releases, and in this like function called onTagChange, it'll like try to lock that feature. So once it's unlocked, all the processes that are waiting on it can go ahead and be processed. Yeah, so this onTagChange, which attempts to lock tag waiter semaphore on a register, that will be unlocked whenever there's a change in a tag. So this enables a process to pause and wait until a register tag is updated, rather than constantly polling for changes. However, there is a small caveat here with the current implementation. Yeah, so right now, polling is triggered by all changes on any slot for any tag for the register, which means that it doesn't precisely match that picture over there, because it'll trigger whenever a change would happen, but it might not be like, oh, this slot has been freed. It can be like, oh, this slot is actually entangled something else, but it'll trigger the loop. So to improve efficiency, we plan to extend this mechanism to allow processes to wait on changes for a specific tag, rather than reacting to all tag updates. As briefly mentioned earlier, tags can also be used as messages that are sent through either classical or quantum channels. Typically, we have a tracker running on each node or register that kind of like listens for those like tag-based messages and takes action based on their content. So for example, for the example I was like talking about, the entanglement protocol, there is a entanglement tracker that listens for tag like entanglement update X, entanglement update Z, and entanglement delete, and applies the corresponding correction. Or I guess for the deletion, it deletes the entanglement if needed. Yeah, so this is pretty important if you want to do error correction protocols. So let's go back to the example I was talking about. And here is the improved version that we pushed, where now we can wait on tag changes before we run find free slot functions. So if we don't specify retry lock time, then it waits for tag change on either node. Okay, so now we'll see how these metadata tracker and synchronization work in a full stack example. So here, what we're trying to do is a 2-to-1 purification or distillation, same thing. That is, we have those red two low fidelity, long range entanglements to begin with, and we want to purify them into an entanglement with a higher fidelity, the green one over here. So instead of using quantum gates, here we're going to be using a technique called measurement-based quantum computing, or MBQC for short. So this purification method using MBQC is based on a research paper by Scikit's group, which is part of Center for Quantum Networks. And I thought this is like a good simple example that kind of like demonstrates how the classical control works in QuantumSavory. So yeah, so as I explained before, we start with 2 low fidelity entanglements. They're long range, so each of them are, like this is register A, this is register B. They're like far away from each other. Yeah, so like between them, they cannot communicate, like say faster than light. To do measurement-based purification, we do need extra qubits. So we need 2 extra on each side. So each register would have at least 4 slots. Yeah, then what we do is we entangle these qubits by creating a cluster state. Basically what we do is we initialize the yellow ancillary qubits with plus state and apply C-phase gate for the lines drawn over there. After that, we can measure these qubits and apply correction. So I'm not gonna get into details on like what basis we have to measure them and in what order and what kind of corrections we have to apply, because it's not like very relevant to what I want to talk about in this talk. But at the end, with some probability, we'll end up with a purified pair here. So let's go over this in terms of submodules, which are small components of the protocol, and also tags. Okay, so first we run entangler, which establishes the initial low fidelity entanglements. between the red nodes over there. When it's successful, it'll tag the slots with entangler counterpart, as before, I guess. At the same time, we also have this subprotocol called ancillary setup, which joins those extra qubits, basically creating the cluster or graph state. Once that is done, we mark it with setup ready tag. So once both of them are established, we finish creating the cluster state as shown. That's like being done during this like purify submodule. And we take the measurements on the top three qubits on each side and apply like the corrections. So once the measurements are done, we mark it with measurements done tag for both register. And so we're gonna have a measurement result for the second red qubit. And we're gonna send the result to the other register through the channel. And we have a tracker which receives the message and compares it with the measurement on the current node. If they match, then the purification process was successful. And we tag the green qubits with purified counterpart. And I guess like if it failed, the measurement results don't match, we kind of like scratch everything and start from the top until we get the successful process. So that was a high-level idea on how to do 2-to-1 purification work using measurement-based quantum computation, which shows how tracking works in QuantumSavory. Okay, lastly, I wanted to share a few ways you can get involved. I guess it was mentioned yesterday as well, but you're welcome to contribute to QuantumSavory. We are running this NSF-funded bug bounty program where you can earn a few $100s by helping us improve the package by implementing new features or fixing some bugs, whatnot. Yeah, so you can find more details on the bug bounty page linked here. And also, we just wrapped up the second quantum numerics summer school last week, and we'll probably having the third one next summer. So if you're interested in participating, you can find more information at qnumerics.com, but that'll be for next summer in a year. Okay, so to wrap up, here's a quick summary of what we covered today. I introduced the classical metadata framework in QuantumSavory, highlighting the tag system, tracker synchronization, and weighting mechanism using semaphores. And we walked through a full stack example of 2-to-1 purification using measurement-based quantum computation, or MBQC, where we saw metadata tracking in action. And finally, we had a quick plug on how you can get involved by contributing to QuantumSavory through the bug bounty or by participating in the Quantum Numerics Summer School. Okay, well, thanks for your attention, and I'm happy to take any questions.
Awesome, thanks, Hannah. Questions from the audience?
Hey Anna, thanks for the nice talk. So I understand you set up a mechanism to wait for specific things to happen in your simulation, in the quantum network simulator. How hard would it be to implement something similar into the concurrent sim lower level discrete event simulator, to wait on certain types of events, for example? Would that be transferable, or?
Sorry, can you repeat that?
So you're waiting on specific things to happen in the simulation, like a specific tag change, for example.
Yeah.
But I noticed in the concurrent simulator that this is built on top of, so such a feature doesn't really exist, which I guess is why you needed to build it. How hard would it be to take this feature and put it into the concurrent simulator, so that you can wait on specific event types, for example?
So if I understood that correctly, you want to use the concurrent sims, like the lock
So for
feature,
example, in
yeah,
concurrent sim, it will be useful if you could sometimes say, like, I want this process to wait for something particular to happen in the simulation.
Right.
But the features for that are kind of limited, and I think that's in part why you had to like build this whole text system to wait for specific things to happen.
Yeah.
How hard would it be to like take this new feature and contribute it back to concurrent sim?
Honestly, like what we built was pretty general, so I think it can just like be integrated pretty easily. Yeah, like it was. I don't think it was anything. There was anything specific to like say, like QuantumSavory really. Yeah, that's a good suggestion.
That would be cool.
Mm-hmm.
Any other questions? I actually have a small one, which is just kind of like, as someone who's trying to get a feel for how these systems are built and scale, like when I think about like having lots and lots of sort of different networking systems that I need this concurrency problem to be solved for, like what are the kind of the key challenges to like simulating larger and larger systems in this kind of framework? That like, is everything as built? Like, does it seem like, okay, things should scale okay, or like there are going to be more challenges as larger and larger systems need to be simulated?
Personally, like the ones I've simulated, I like never ran into like a problem where I had to like wait for like a really long time. Like mostly because I didn't really get to work on like a very large system. Yeah, I am not sure.
Okay, yeah, well maybe we can talk more offline, because that would be interesting to hear. Okay, well if our audience is okay, I think we maybe can take a short break, let our next speaker set up, and 7 minutes or 5 minutes or so. Yeah, perfect. All right, let's thank Hannah again, and take a short break.